Hello everyone, so in the previous video I showed my results of a new state-of-the-art algorithm called NeRF, the Neural Radiance Fields. And then I got comments asking of a tutorial of how to use this algorithm. So this video is for that purpose. Alright, to start with, let me give a short introduction of what NeRF is. So what NeRF is able to do. So let's write it here. So NeRF is a view synthesis algorithm. So what is a view synthesis? So let's give a concrete example here. So imagine that you have an object located here. For example, it's a ball, a blue ball. And then you took photos around it. Let's say you took photos from this location. So this is your camera. And then you took another photo here, and so on. So this algorithm NeRF, it will leverage these photos that you took, a limited number. And then you can synthesize new views. For example, you want to know how this object will look like if you place a virtual camera here. So this is a virtual camera. So this algorithm allows you to learn from these videos, from these photos, and it learns a representation of this object, and it allows you to synthesize new views from a different angle of view. For example, here. So by using this, we can virtually place cameras here and here, so to make a full 360 degrees video, as I showed in the previous video, like this. So these yellow cameras are all virtual cameras. And then we are able to synthesize views for all these cameras using just limited numbers of photos from these real cameras. So this is what NeRF is able to do. So it allows us to synthesize new views from limited number of views. All right. So that's a short introduction of what NeRF is. So if you want a more detailed explanation of NeRF, you can watch 2-minute papers video, which is also a great video. I'll post the link in the description. All right. So let's stop the introduction and pass to the tutorial. So first, go to my GitHub here. So I'll also post the link in the description. So it's called NeRF PL. So PL stands for PyTorch Lightning, which is the framework I use to implement this. And then go down, can press here. So I provide colab notebooks to allow easy usage. So originally, this algorithm is like any other deep learning algorithms. It requires GPU and also Linux operating system. But if you use colab, it allows you to use this algorithm anywhere, even on your Windows PC or even without any GPU, because it runs this algorithm on Google Cloud. So press here colab. So first go to this NeRF NeRF notebook. So press here. And then you will see a button open in colab. So just press this. All right, it takes some time to set up for the first run. And then can press here, the folder button here. So it says it's still connecting to the runtime. So let's wait a moment. And to start with, let's try to reproduce what the original authors do. So this is the original repository. It's called NeRF from B. Miles, which is one of the authors of the paper. And then, so they did a lot of experiments, one of which is this scene. So this scene is called fern, which is a plant. So let's try to reproduce this result. So go to our notebook here. So the first thing is to install the code, which is my repository. So you just need to execute these cells. So you can press the run button here, or you can press Shift plus Enter. And for the first time, it will pop up a warning saying this notebook was not authored, but you can just run anyway. Then it takes some time to clone the repository and do some installation thing. Right, so let's wait a little bit. Alright, so once the installation is done, the next step is to prepare data for training. So to prepare the photos. As we said, we are first trying to reproduce this fern scene. So we need to download the data from the author's page. So to do that, just go to my GitHub repository again, and then scroll down to this LLFF part, and then click the link here. So it will link to the author's Google Drive. So now we need to include this folder to our Google Drive. So to do that, we don't need to download this folder and upload to your drive. We just need to right-click on this folder, on this NeRF LLFF data folder, and then click Add Shortcut to Drive. This will add a shortcut to your Google Drive. So select your drive and then select wherever you want to locate this folder. So for example here, and then you click Add Shortcut. After that, you will find a link on the folder you selected. So as I did here. So once that is done, then go back to the notebook and then execute this cell, which will mount your Google Drive. So the first time you execute this cell, it will ask you to enter your authorization code. And you just click this link that appears here, and then copy the authorization code and paste here, and then press enter, and it is done. So after that, you will find your mounted Google Drive here. So you click this folder to go upwards, and then you will find it under this content folder. So now this content folder will consist of everything. It will include everything that you have on your Google Drive. Alright, so okay, now the data is prepared and we already installed everything. So the next step is to train. So to train, just execute the cell here without any modification. Alright, sorry. There's one modification you need to do, is to modify the directory where the data is located. So you need to change this path to your fern path. So in my case, it's located under my drive colab, NeRF, and NeRF LLFF data and fern. So it's located here. So I set the path to this path. If you downloaded a folder to another link, just change it here. And then you keep the other things fixed. And then you execute this cell to start training. So just press this run cell or Shift plus Enter. And then it will display the training progress in this console. So I'll just show you the first steps of training because it will take a long time, so I won't wait it. All right. Right now it starts training. So you can see the loss is decreasing, so it's good. Right, by default, it will train for 30 epochs, which will take like about 5 to 8 hours, even on this notebook. So you need to patiently wait. Right, so I won't wait it here because I have already trained this scene. So once it is done, or you can stop it anytime you want by clicking this stop button. So I'll click it now. So once the training is done, you can then move to testing. So to create a 360-degree view like here. So to do that, just execute this cell. Alright, there's one modification you need to make, which is here. You need to modify the checkpoint path, so which is where the model is located. By default, the training that you just executed will generate checkpoints under this folder. Check CKPTS and fern. It will generate checkpoints here. Or you can download my pre-trained model here. So click on the releases and you can download the model here and import to your Google Drive. And then modify the path here and then execute this cell. Alright, I'll show you what this cell produces. So first go to this link and then download the model here. So click this. It will download model and then you upload it to Google Drive by pressing the upload button and select the model. And then you can drag the model to the folder content and just modify the path here as epoch, for example, 29 as the name here. And then execute this cell. So this cell will produce all 360-degree view of the scene under the folder results LLFF and the scene name, which is fern. So it will produce the results on the results LLFF fern. So it will first create these virtual images, and then finally it will produce a GIF file combining all the images. So it takes some time. As it says here, it will take about 20 minutes. So we can first inspect one of the files. So this is the first virtual image that it produces. So it looks decent. Alright, so I'll stop it here and show you the final result. You will need to wait until this finishes. Alright, once the testing finishes, we will have 120 synthesized views that will be generated under the folder LLFF and fern. And at the end, you will have a GIF file that combines all these synthesized images. Now you can download this GIF file by right-click on the file and click download. And if you open it, it looks like this. So it's exactly what I pasted on my GitHub Markdown. Alright, so that concludes the training for the author's provided data. Now I think many people want to use this code to train on their own data, as I did here. So this is a figure with 360 degrees of synthesized views, as I showed in the previous video. But before training, I want to give you a short guideline of how to take good photos. So as you know, to train a good model, we must need to have good training inputs first, so good training images. So now I'll show you what I did at the beginning, which was a failure. So at the beginning, when I trained this model for the first time, I placed the object, so my figure, on top of the table, which was exactly what you saw here. So I placed the object on the table, then I took photos from different angles. For example, here, here, and here. It was actually a 360-degree surrounding view, but with only sparse inputs. So I only took 32 images. So, but why do I say that was a failure? It was because For example, when I took the photo from this angle, from this camera position, not only did I capture the object, but also I capture a lot of background stuff. Like I had a chair which was here. So by placing a camera here, I also capture a lot of these random backgrounds. And for example, if the camera is here, I capture another random thing. For example, I had a small table here, and then placing the camera here will also capture these random things that was not the object. So as a result, I find the training result very glitchy. Like you can see here, there is a lot of small noise, like you can see on the top part of this image, which I found not that desirable. So this was, I think, a failure. So don't do this. What I tried at the second attempt was that I placed the object instead of on the table, but on my bed, which was a lot larger than my table, of course. So this is my figure, and I placed the object on the bed. Then I did the same thing, so I took photos from these 360-degree surrounding views. But the good thing is that this time when I place the cameras at these positions, I only captured the object and the ground, which was my bed. So there is no any random background appearing. You can see my training photos here. So this time I only captured the object and the bed. There is no random thing behind it. Right, so these are my training photos. Then I find the result to be good because there is no random background appearing in this setup. So capturing only the object and the ground. I find this to be crucial to train the model. Right. Once you guarantee that your input photos were captured in this good way, you can now start training. So to start training, we need another notebook, which is this colab notebook. So open this notebook, which you can find also under this colab section, and then click open in colab. And then, all right, the first thing to do is also installation. So just execute these cells. I won't execute it now because it will take a lot of time, like almost an hour. So install these things. And then you need to upload your photos to your Google Drive. So to do that, just open your Google Drive. And then open the folder you want to upload it. So I uploaded my photos to this folder called Silica and Image. You pay attention, you need to create a folder called Images under the name of your scene. For example, the figure's name is Silica. So I create Silica and I create a folder called Images under it. And I placed all the photos under this image folder. It's very important. And then you can mount your drive by executing this cell. And then now, why we need this colab notebook is that to train on your input data, we must first know what are the relative poses of your cameras. So for example, if I place myself on a bird's eye view, so this is my object and these are my input photos. So input camera positions. So the important thing to know is Now we need to compute the relative poses between these cameras. For example, we need to know how much rotation and how much translation is there between these cameras, between these two and between all pairs of these cameras. To compute that, we need to execute this colab notebook. That's why we need this. All right. So now you can execute the next cell and then run colab. So the only thing you need to modify in this notebook is this folder. So modify this folder to be your data folder. So for example, mine is called silica. So I modify this path to silica folder. So pay attention, your images must be placed under this images folder, not directly under the silica folder. So under this images folder. And then you can execute this cell. If it runs successfully, it will display this information. For example, it says that there are 65 images, and then it is done. All right. So once this is done, you will get additional files here. So originally you only have this images folder, but after running this cell, it will create other folders like sparse and database, and then poses bounds. So once you have these files, you can start training. Then you can close this notebook and go back to our NeRF colab. This time, instead of running this forward-facing scene, you run this 360-degree inward-facing scene. By modifying the path also. So you need to set your directory. So set this path to this path. So silica in my case. And then set your image width and height. And the other things I don't think you need to train. You need to change. You can run as default. So after you execute this cell, it will start training. And the rest is the same as what we got when we train on the NeRF, when we train on the fern data. Alright, so that concludes also the training for your own data set. After that, you will also get a GIF file like this. Lastly, this NeRF algorithm can not only synthesize novel views as lists, but it can also learn a 3D representation of the object. You can find on the author's project page that they extract a 3D mesh representation of a Lego toy. You can drag and rotate it around. But you can see here the reconstructed mesh is all white. There is no color. So many people are asking in the issues of how to add color to this reconstructed mesh. And then I finally come up with a way to add color to the mesh, as shown here, for example, for the Lego toy, and also for my own model. So in the next video, I'll show you how to add color to the reconstructed mesh. Of course, how to reconstruct the mesh first, and how to add color to it. And then I'll also provide a notebook of doing it on Google Colab. Alright, thanks for watching this video and see you next time.